Well, welcome back. Good to see everybody again. All you committed students ready to work hard. Still look like you're active and well rested. That'll change soon, I'm sure, as our first round of tests come in. And you hit the wall and it continues on till May. But remember that it will end in May. But as we get started in the second week here, let me just focus your attention again on this first unit that we are doing. Remember, the Physics 123 is a little different structure than the other physics classes you have taken with me, in the sense that we go from topic to topic to topic. And as I pointed out at the beginning here, is this first topic is really about oscillations and waves. And as you know, the first homework and the first chapter assignment that you did and you're turning in now, it was on oscillations. We're going to continue that into waves, but as I pull out the syllabus, this first section is designed to go pretty quickly. We're really trying to pound out 4 chapters really quick. Fortunately, they are short chapters. I think pretty easily digestible chapters, but can have a lot of words inside them and a lot of information. It's hard for me to get them out all that quickly. Of course, that's why I went ahead and put a bunch of definitions on the board to save a little bit of time. But also, as you'll see here in the lecture, there's formulas, 2 formulas in particular, that your author works out that I'm just going to say, okay, here's the answer. Let's talk about the answer. I'll let you look at the details. It's not exactly what I like to do, but it's my way of saying here, we're only committing 1 day to this chapter. And next lecture on Thursday, we will go into chapter 17. So we're going to go kind of quickly, if you will, through here with the idea that hopefully our time in class will be spent well on, and then I tried to focus on things that I thought would be better than what I was talking about, and other things like deriving a couple of equations or writing out the definition, I would leave to the book and let you read them. So that's the way I'm trying to manage the time, and just wanted to point that out, that as we look here, look what's coming up here real quickly. It's the test, or half test, if you will, on these 4 chapters here. So that's what I wanted to say here at the beginning here. It is, well, maybe I shouldn't get the date. It's the 19th, so it's February 19th. It's not next week, but it's the week after. So it's 2 weeks from today, and that's why we do 16 today. We do 17 on Thursday, and then we do 18 on next Tuesday. And then we'll start into 19 and go at a little more normal pace, where we do 1 chapter a week as we get into our thermodynamics, where it really needs 1 chapter per week here, whereas this material perhaps not. All right, well, all that is to say here is, here's what I'm going to try and do. I just want to talk about waves. You'll see, hopefully, that the material is straightforward. There is some mathematics. Most of this, though, is concepts, and it is mechanical waves. It is a chapter, like I said, that starts off by just what are waves in general. Next chapter, we will get into sound waves in particular. We will do a particular type of waves. We will deal with waves in this sense. We will put waves on this string. We will put waves on what we call this little wave machine. This is my favorite one there. You make a little pulse and it sends it down and it goes back and forth. And so the beginning part of this chapter here is just simply this question: what is a wave? And what are the words we use to describe a wave? And that's the first section, and what I want to go through there. And so this is terminology, definitions, if you will, here. I'll start off with a kind of a layman's definition here of a wave. I would call a wave something physical here that has the transmission of energy, but not the material or matter itself. And this is where we call it mechanical waves, because they do have the same mechanical properties. They're made out of solid objects like this, where, look, here's a bunch of rods. And these rods are just kind of balanced with a metal piece down the center. But when you make a little pulse on one, that is when you pull that first rod up, the first one pulls the second. So it gives all of its energy to the second, which gives it all to the third, which gives it all to the fourth, to give it all to the fifth, and so forth and so on. So eventually what happens as we get to the end here, we would say that over here, the energy transmitted to here, right? If we were looking at, say, potential energy, if there was something on the end of this rod, a little weight, or maybe a little ant sitting there, that would lift the ant up, right? The ant gained some energy. The energy went from here to there. But did the material itself, did the rods move? Now, I guess I should say they moved up and down. But did they transmit from left to right? They didn't, did they, right? And that is where we get started. That is what a wave is. And you can see why this chapter follows the last chapter, because in the last chapter we did oscillations. You could imagine if I didn't have a bunch of other rods on the end, if I only had one rod and I pulled it up and let it go, you could probably sit here and see it oscillate, right? Up and down and up and down and up and down. And so there's our oscillatorial motion. And so you can see that this is just an extension of that. That's why the words we're about to use are just an extension of the words we've already used in the last chapter. Of course, that's why you'll see a lot of the same words. They might be applied a little bit different, as you'll see. Words like period and frequency we already saw. We're going to see them again, and they essentially mean the same thing, slightly different depending on how you are viewing it. You can view it with oscillations or with the transmission of energy. So there's a little bit more to waves than oscillation. Of course, that's why it's the chapter that follows oscillation. So we go from oscillations to the transmission of that oscillation. So that's what we want to keep an eye on. We want to go, is this a wave? And so the answer is, did energy transmit in that case? Yeah, that's a wave. Did energy transmit in this case without material transmitting? Yeah, that's a wave. Here's one. How about this one? I take the rods in a vertical one, and I know they're set behind here, but I hope you can see this one back here. Instead of the rods laying out horizontally and vibrating them vertically, what happens if I push on this one? Did energy get over here? Did material go over to here? No. Is this a wave? Yes. It is a wave. Now, granted, it's a little different looking wave than over here, but it is still a wave. It's a mechanical wave, and that's what we'll be dealing with, mechanical waves, which is why we won't get into optics until Physics 122. Yeah.
What about oceans? Like, there's a wave on the ocean, so technically the material doesn't move.
Okay.
So how can things wash up on shore if the material doesn't move?
Well, it's part that, but part more complicated. There's wind blowing things if they're on the surface. There's current blowing it. The water does move once the wind breaks, if that's what you're getting at too. I know when I play fetch with my dog, and if I throw it out past the breakers, the tennis ball doesn't come back. But if it's fine, you see what I'm getting at? It just sits out there and goes up and down with the waves. But if I throw it inside the breakers, then it does hit the breakers and rolls back in. So, yes. Right, and then eventually, depending on which way the current's going, the current can bring it inside the breakers, and then it comes in. Or, unfortunately, there's been many times where it goes out. One time in particular, I thought my dog was going to be shark bait. It's like 45 minutes later before I got the dog back in here. But it just kept going out there. Like, it's not that important. It's just a tennis ball. But I don't know if that helps you. But then another part of this, as we'll see here, and your book has a really good picture on it, is there is, now remember, I did this, which is up and down. Getting ahead of myself, that's a transverse wave. But this too, you just told me was a wave. And isn't that forward and back? So waves can be moving in this pattern, which is forward and back. And water waves have a component of both this and this, depending on how deep they are. And so there is that. And you probably know, because you've been in the ocean, no doubt, that when you're in there, you move, and then you move, and then you move, and then you move. So the ocean wave has a motion this way, like this one, which we will soon call longitudinal wave, and it has motion this way, which we will soon call transverse wave. Well, hopefully, let me keep going here, but let me do this. Is this a wave if I make a little pulse? Would you call that a wave? Sure, right? There's the pulse. Did energy move? Did the material? No, right? That little piece on the slinky, or the spring, whatever you want to call this thing, is still there, right? And so that's this intent. And so as we look at waves, we're going to be very abstract this chapter. That's good and bad. It's good because we're going to learn this broad spectrum of things about waves. It's bad because you're going to go, oh, but how does that apply? What kind of waves are we talking about? Are we talking about waves made up of these rods? Are we talking about waves that are on a string? A spring? I mean, what are these type of waves? Well, next chapter will be more specific. Next chapter will be about sound waves in particular, which again is why the next chapter can be pretty short, because we're going to take everything we learned in general about waves here and apply it specifically to sound waves in the next chapter. All right, so that kind of gives you the heads up of where we're headed this week. All right, so let me make a couple of waves here. Let's look at a couple of these answers here. Like I said, we've got different machines out here. This is my favorite one. It's slow enough and big enough that you can kind of see. If I were just to do this would be a good example of mechanical waves. Okay, and so they kind of curl up, they arch around. But did you see how the crest was kind of moving along? What's the crest? All right, so there's our first definition here. So drawing a level line for those rods or a level line for the water. If I go out to the pier and I look, I will see this hump right there, another one behind it, and I will see that hump moving in, right? That hump, the highest part, I will call the crest. All right, down here, the lowest part of the wave, I will call a trough. So there it is, the trough. All right, so again, just so we can get some terminology there, that's the highest part of the wave, the lowest part of the wave. Next thing, amplitude. Well, again, we used that word last chapter, really kind of means the same thing. Of course, these are moving along, and that's where visually it gets a little bit different. But let me make these waves again. Let me have you just look at one rod by itself. And when I make a series of waves, of course, I think your focus is on watching them move. But if you were to look at one rod by itself, wouldn't that one rod just be going up and down with simple harmonic motion, this oscillatorial motion we've been discussing from the last chapter? Fair enough? All right, so there's really kind of two ways you can view a wave. You can view it collectively as all these pieces moving along, or individually you can look at one rod going up and down, and then we're back to our oscillatorial motion. And with our oscillatorial motion, didn't we call the maximum displacement that rod goes up its amplitude? But if you look closely, if you combine those two views together, if you say, watch this wave as it goes along, if you focus on just one of them and you look at how high it goes, isn't how high it goes the amplitude of that one rod, but isn't that also the amplitude or the highest that the peak of the wave is? Exactly. So not a surprise that this right here is still called and still labeled the amplitude, right? How high is its maximum displacement? At any moment it may not be at its highest point, but it still is its highest point. So again, hopefully goes without saying, its amplitude, we'll use the same symbol that we did, would be in units of meters. Here's something we didn't have in the last chapter as we begin to look at this, wavelength. Well, what's the definition of the wavelength? Question.
What about the one in the back? It's trough, crest,
Tell you what, remind me that when I get over to here. How's that? Okay, yeah. But we'll give it a crest and trough also, depending on our coordinate system. But all right, but let me focus on the easier one first, because transverse waves are a little easier to visually see, so I'll start there. But the next one is the wavelength. Look at the definition. I think you already know it from the Physics 102. It says here, what's the minimum distance between two identical points? So up here in this picture, what would be the wavelength? Yeah, so from crest to crest is one good example of a wavelength. trough to trough would be another good example of a wavelength. Whatever that distance is needed to repeat itself. It could be this part of the wave, which is at equilibrium, if you will, going down. So when I get to here, that's not a wavelength, that is equilibrium again, but way up. So let me go here. There we go. There it repeats itself. So here to here would be a wavelength, here to here would be a wavelength, here to here would be a wavelength. But that's it. It's wavelength. The new symbol for us, if you're not familiar, we like to use the Greek letter lambda for the wavelength. And of course it's a length, so it would be measured in units of meters, right? And so that's the, like I said, the first section here. What's the vocabulary here? Wavelength. It's a distance. Please don't confuse it with period. What was period? And they're pretty much the same here between last chapter and this chapter, right? Period was what? The time to repeat itself. If I had something like that rod oscillating and it goes up to here, okay, and I start my watch, how much time does it take to get back up here? Right, it's the time for one cycle, right? Now, if you're watching this wave, it's really kind of the same thing. If you look at two crests here, okay, the reason that second crest is there is because if you watch that one rod, it would be up here. That one rod goes down and then comes back up, right? So the time it takes for one rod to go down and back, what we called period last chapter, is really kind of the same thing that we would call period in this chapter, because the period would be the time. How long does it take for, if I'm at one crest, how long is it going to take for that next crest to get to me, right? And of course, the reason that crest gets to me is because what happens here is this one goes down and then back up. It has the appearance of this hump moved along. Now, did any material actually move along? No. So the period, the time, as it says here, the time required for two identical points. Okay, so the crest to pass a given point. So if my given point is right here, the period is how long will it take for that crest to get to here? And I'm trying to point out that would be the same as the time it would take for the rod to go down and back up in terms of an oscillation. So we used the word before last chapter. We're going to use it again. We're going to use the same symbol. It's measured, of course, in seconds, and it is a cycle. It is the time for one cycle. And please don't confuse it with the distance, right? We didn't have this one. This is the time to repeat. This is the distance to repeat. Tied together, no doubt. Again, frequency, same thing. We could view it a little bit different here as we're looking at things moving along as opposed to just oscillating, but hopefully you will see the connection here. What is the definition of frequency? Well, last chapter, it was the number of oscillations in a given second, right? Or a given period of time. Usually we use seconds. That's where the hertz came from, right? Number of cycles per second. And I would say it's really essentially the same thing. This says the number of identical points that pass a given place. For example, if we're back here at this given point and we watch this crest come by and another crest come by and another crest come by. Let's say 3 crests come by in 1 second. I would say 3 identical points. 3 crests came by in 1 second. I would say the frequency is 3. But of course, if I was just looking at the oscillations of this rod, that would mean this rod went down and back up, down and back up, and down and back up. That rod went under 3 cycles. And so see how they're really one and the same? Viewed a little different because we're kind of viewing it as if something was moving along, although it's not really moving along. The shape is moving along. The material is not moving along. The energy is moving along. Fair enough? And so again, that's this beginning section. What are these words? And a lot of them are the same for oscillations. They're tied closely together. In fact, so much so that I often feel like students don't really get the difference between last chapter and this chapter. And it's easy to kind of miss that. But there is a difference, because in the last chapter we just looked at one object just oscillating. It just changed with time. This is a bunch of objects that are oscillating. It's like it's moving along. So we're going to see this is a function of both time and space. And there's motion to it. There's at least motion to the shape. So again, this amplitude, this period frequency, essentially the same thing, slightly different view because we're viewing things moving. Well, last 3 definitions. A wave pulse, that's really this. What I've been showing you is a pulse. One little single hump or bump here, and it just make it travels along. Whereas what we'll see here is a wave. What we really mean by a wave, not a single pulse, but a wave keeps repeating itself. You can see that in what we've been saying. The time to repeat itself, the length to repeat itself, the number of points that pass a given time that repeat itself. So truly to make this a wave, I would have to keep repeating the same thing. This is a wave. And of course, then it bounces back, and I have all kinds of other issues that we want to talk about soon here, but I'll stop there. But if I kept going and you kept watching this repeat itself forever and ever and ever and ever, that is a wave, as opposed to a pulse. This is a pulse, a single bump, a single click. So small amount of semantics there, but important, because you're not going to really have then a wavelength with a pulse, right? It just doesn't repeat itself. It is just one little hump. Although chapter 18 we'll see some other things that we'll describe that wave pulse. And then the last two, which leads to your question, what is a transverse wave and what is a longitudinal wave? Well, again, if you're remembering from the 102, the transverse wave is simply this. Whatever is making up the waves. And so again, remember, we're talking about waves in general. So the bad part about this is we're kind of general. We're kind of abstract about it. But the medium. All right, so if this is water, then I'm talking about the movement of the water molecules. I don't have any water here, but I do have these rods. So my medium is those rods. And so a transverse wave is where the rods, the particles that make up the medium, the rods in this case, move which way? Perpendicular to the wave motion. Well, what's the wave motion? Well, the wave motion is the direction the energy goes. So again, looking at this, which way would you say the energy moves? Now, okay, horizontal, left to right. Which way are the rods vibrating? Up and down. And so this is a good example of transverse waves. The oscillations, up, down, are perpendicular to the flow of the energy, the motion of the wave. This too is a transverse wave. It's a little faster wave, but it is still a transverse wave. They oscillate perpendicular to the direction they travel. In this case, they travel horizontally and they oscillate vertically. But this other one back here that I have fits this category. What is a longitudinal wave? Now, here are the particles, and in this case, these rods again. The disturbance is parallel to the motion of the wave. So again, as I bump this and I ask, which way does the energy travel? Horizontally. Which way do the rods shake? Horizontally, right? And so the disturbance, and if I kept doing it like this, I would have a wave, and then it would reflect back there, and I'd get a pattern, and more on that in just a second. But that would be my wave. And there would be things like a wavelength. Harder maybe to see. When I push this one, I would have to go over to here to find out where is the same place as this wave. That would be its wavelength. Your earlier question is, how do you define the crest and the trough? Really, it's on your coordinate system. So if you were to look at this at one moment in time, you may say, and even though I'll put it on a vertical axis, those rods didn't move vertically, they moved horizontally. Fair enough? All right, so if this part of the wave is moved away from its balanced or equilibrium point, I'll put it there. And then as I go further, this one would be moved a little bit less. And then this one would be moved a little bit less. And eventually I'd get to one here that's not moved. And then I would get to these guys, which are now tilting that way. And so they're moved in a negative direction. And so this is, less than 0. This is greater than 0. And now when I draw it this way, this would be my definition of a crest and a trough. The trough would be the negative movement. But of course that was a choice of coordinate system, so I could have said it. But I guess that could also be true about your vertical. Right? And so hopefully that helps. Well, I wanted to pound that out real quickly in the first 15 minutes. I think I did. And I think a lot of that was somewhat known by you, but I'll say it again. I just wanted to really get that focus that this is a step up from what we did in the last chapter. The last chapter was just an oscillation of a single rod. And so we would look at things, well, how much time does it take for that one rod to get back to itself? Whereas now, with a whole series of rods oscillating, we're saying how much time would it take for that crest over there to get to here? And it really is the same as if I am at a crest watching this rod go down and then back up. And so, but my focus is a little different. How much time does it take for that crest to get here? Did you have a question? No. All right, so with all that behind us, now we can go forward and into the math. Because as you have probably realized over and over throughout these semesters is we took a lot of this same physics in 102. That was our basic physics class, and we learned these ideas. And all these words we saw in 102. We also have learned a lot of math. And the goal of this course, the calculus-based physics, is to integrate those two together, to take your basic physics together with your math, put them together, and do some more advanced and complex problems here. So I will start with this question. Any relationship between period and frequency? Yeah, not a surprise. It's the same thing we saw before, right? Now, granted, we're looking at frequency and period slightly different, but they, of course, are connected to what they were last chapter, so the math should be connected. So my first equation for the chapter would be, if you know the period, you also know the frequency. Fair enough? They're just reciprocals of each other.
So when light enters water, does the wavelength change or the frequency?
The wavelength will change when light enters water was the question. But I'll also be clear to point out here, this section is, well, it's waves in general. So in that sense, we can apply them to light waves. But light waves are not a mechanical wave. So as you'll see in these next 4 chapters, I will never really study light. I mean, they might make good examples because they are waves and they have wavelengths and frequencies. But you might remember from last semester that the energy is associated with its frequency. So as it goes in, it doesn't change its energy. So conservation of energy means it has the same frequency. So as its speed changes, its velocity. I mean, since its speed changes, which is the next equation, by the way, its wavelength changes. Yeah. We do have the unit on optics coming up, though, in a few weeks. Yeah.
Sound wave, is that longitudinal?
Sound waves, as we will see on Thursday, is one molecule bumping straight into another one. And so next Thursday I will have this machine out telling you that sound waves are longitudinal waves. Molecule, boom, 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 hitting the next, hitting the next, hitting the next. And so that's how you hear my voice, is my vocal cords hit the molecules, which hit the next, which hits the next, and then hit your eardrum. Yeah. All right, so there's the first math equation. How about the speed of these waves? V, what speed are they traveling? And part of this is also to be real careful here. There's 2 speeds going on. Did you catch that? Watch this. Do you see the 2 speeds? I mean, one, I'd say, is the speed of the wave, the speed of the energy, right? The wave is, what speed does that energy flow? But what else is happening? The rods are moving up and down here, right? Now, I'll put that off to the side because that's just oscillatorial motion. Don't we know the equation for the oscillatorial motion? Wasn't that what we just did in 15? Maybe I'll put a little subscript y down here to say, look, this is the velocity of the rod. Or maybe I'll even put rod down here to say, look, this is the velocity of the rod. Because the way we wrote it out was this. And when we took its derivative, we got this. And so we couldn't just say in the singular, what is the speed of the rod? The rod changed its speed, right? As it was oscillatorial up and down, as it went through equilibrium, it's going very fast. As it gets to the end points, whether down or up, it was slowing down. And so there was a sinusoidal pattern to its speed. I'm not talking about that, but I don't want you to forget it either. What I'm talking about is the speed of the crest, the peak as it moves along, the shape of the wave as it moves along. Not the rod, not the material itself, but the energy. What is its speed? And you can kind of see in this demo that it is a constant speed. And maybe not in every case, but in the simplest case, and that's all we'll deal with in this chapter. We'll just deal with waves that they go the same speed all the way through the medium. They may go into another medium that change their speed, as we will see real quick as we go from one medium into another. But in that medium, let's just say, as they continue through that medium, they have a set speed. Fair enough? So that's what I'm talking about. I am talking about the speed of the energy. Here. All right, well, maybe you can see it here, just going back to our mechanics and using these words here. Let's see, speed would be, if there's no acceleration, it would be just distance divided by time, right? So, again, going back to a certain point, like right here, I could stand here and say, all right, right now, say I'm at the beach standing here, here comes the wave. Here's the crest of the wave. It just passed me. And I will start my watch, and I will time it till the next crest gets to me. Well, how much time will it take from crest to crest? That's the definition of the period, right? Now, it would be different for different kind of waves. Water waves would probably be different than sound waves, which would probably be different than that. So I don't want a numerical answer, but I want a conceptual answer. It would be the period. That's our definition of the period. So when I come over here and say velocity is distance divided by time, the time is represented with a capital P. What is the time for the next crest? I'm standing at a crest. What is the time for the next crest? That's the period. How much length did it travel? Lambda, right? That is our portion of our wavelength. And so our second equation is this, that the velocity then for the wave would be its wavelength divided by its period. You know any two of those, you can find the third, right? In fact, let's put those two equations together. Notice that I've got the reciprocal of the period. If I put that together with frequency, what do I get? Yeah. And so wavelength times frequency would be velocity also. And so there's my third equation for this chapter. What is the numerical relationship between these four parameters here? And so, algebra, haven't done really any calculus yet. We'll do some. Not too much calculus in this chapter, but there's one really good homework problem, but we'll wait for that one. We'll wait till Friday afternoon when you go ask Don about, how do you do that? All right. But there's our first three equations. Let's look a little bit more at math here for a second. Let's, for the sake of discussion, say I make a little pulse. Maybe it looks like that. Now let's just take a snapshot of it. Let's just say at one instant time, right when I made the pulse, I took a picture of it. All right. It probably looked like this. If right where I make it, I will call it that the origin. I don't know if you want to call that the y-axis and then the x-axis here, something like this. But if I were to take a snapshot of this, maybe it looks like this. We won't worry quite yet about the exact mathematical equation of that shape. We soon will, but right now let's just say it has that shape. I'm just going to draw a rough shape. And if I call this time equals to 0, what would it look like a moment later? Well, I'm trying to illustrate that the wave would have its same shape, right? But shifted over. And let's let that be our definition. We will have this wave, or this, in this case, a wave pulse. It'll have the same shape, but moved to the right. Could have gone to the left. We'll talk about that soon too, but let's go to the right. And so this would be some time a little bit later. Let's call this time t1. And of course, a little bit after that, time t2, what are you going to get next? Well, again, same shape, moved over. So here's my question for you. It's a math question again, as we are working with the math. How would you mathematically describe something like this? Something that has the same shape, but moves over to the right with time.
Phase shift.
Okay, go on.
So it's it's a sine wave just shifted out of phase.
Well, I'm not sure I'd call that a sine wave, but
Unfortunately, the sine waves shifted out of phase.
okay. Let's see, I don't want to answer that. Let me stay away from the sine wave. It could be a fraction of a sine wave. But if I said Gaussian, how's that? Would that mean anything to you? No? Maybe I... good. You're seeing it. And I'm not sure how best to write. I'll tell you what. I'll do it both ways. I'll do it more for a specific case and an abstract case. This, e to the minus x squared. Is that okay? You ever seen that function? No? You don't. So do you know what that one looks like? Looks like that. And it's got a fancy word called Gaussian. So when I said Gaussian, you didn't seem to recognize the word, so then I thought I would try if you recognize the equation, right? All right, but the square is simply meaning here that I think you know what e to the minus x looks like, don't you? Decaying exponential, right? And of course, if you have a square, you never have any negative numbers like here where it explodes. So e to the absolute value of x would do that, right? And then if you square it, it kind of just gives a rounded shape to it. All right? All right. So I'll use that as an example, but I do want to be a little more abstract, so I'll get away from a concrete example, but that's a Gaussian. Maybe that's worth taking our time to say. That is a Gaussian function, very useful function.
Is it the same shape as the bell curve?
Yes, and it's a shame, you might recognize it as a bell curve. Yeah, yeah. But here's what I'm after. If I were to write this function as e to the minus x squared, or in more general form, f of x, okay? What would I put down here? What would be the difference? And maybe as a reference, why don't we call this x1? And a reference here, x2. And what you pointed out really is, how do I represent a function that is shifted over on the x-axis? That's really my question, right? And I think you know. How do you do it? Yeah, that's where the shift comes in, right? That's what you were saying, the phase shift. We did the same thing with the sine curve last one, where we shifted on the x-axis. We imagined pulling the axis from here a distance of negative x1. Okay? And so all I'm trying to remind you, or teach you if you ever thought about it this first time here, is for something to have the same shape but shifted over, it must have the same functional form, but the argument has been shifted by a distance of x. And by extension of that, how would I write the function down here? Well, I guess that would just be shifted over to x2, right? And so all I'm trying to do is remind you of how do I, using my functions class, I guess that's algebra, how do I represent a function that has the same shape that has shifted over? Because, isn't that what I really have here? Same shape, shifted over. But now it's shifted over with time. So let's continue with this. How would I represent this a wave that is traveling with a speed v? Well, aren't you really saying here, then the position, whether it be x1 or whether it be position x2, is that, velocity times time? So let me put that into these abstract equations. And I told you it was going to be a little abstract. But what I am trying to get you to see here is for something to mathematically be a wave, you would have to have a function, and inside that function, you would have to have position and time, and they would have to be written in that form. Does that make sense? Let me see if I change it a little bit. What if I had written the equation f, which is a function of space and time, and I had written it as e to the minus x squared multiplied by t. Is that a wave? No. Why not? Well, let's plot it at time equal to 0. What do you get at time equals to 0? Now here's the Gaussian times 0. So I get nothing, right? Let me plot it at 1 second. What do I get? Time equals 1. What do I get now? I get that, right? Let me plot it at 2 seconds. What do I get? See what I get? What I get is something looks like a growing mound. It does not look like something that has a given shape and moves. Fair enough? The reason why is what's the requirement to be a wave? That's what I'm after. Not every function can be called a wave. In order to be a wave, it has to have a certain shape. It can have any shape it wants, but it keeps that shape and then moves. The requirement for that to happen is a shifting along the x-axis. And a shifting along the x-axis, the x and t have to be connected together in that fashion. And so what we like to say then is think of any function you want. As long as it has a function of both space and time, and they are connected together. So space and time, and more than that, x minus vt, now we have a wave. This is what we're going to call a wave equation. An example of a wave is this Gaussian wave, e to the minus x vt squared. That is a wave. How do I know it's a wave? Well, does it have x and t in it? Yes. Are they connected in such a way that it would keep its same shape and move with time? Yes. How do I know that? Right here. Fair enough? So, would this be a wave? No. Very few functions would fit this profile. Of course, we're not going to talk any about what is not a wave in this chapter. We're only going to be dealing with ones that are a wave. Let me give you another example here. Would this be a wave? 1 divided by x minus vt squared plus 7. Is that a wave? Yes. How do I know that? It fits the wave equation, doesn't it? What's the wave equation? The wave equation is this. Any function that is both a function of space and time, and yet the space and time are connected in a very special way, so that what will happen is it will have the same shape of the function, just shifted over later on the x-axis. Fair enough? In fact, maybe I should draw these pictures. This is what we usually call a Gaussian function. And so this is the bell-shaped curve we were talking about. This is what we call a Lorentzian function. It's kind of got that same look to it. It's a little narrow, a little taller in its fashion. And you can kind of see at x equals to 0 and time equals to 0, it peaks as 1/7. And as it shifts over with time, there would be some positive value of x along with some positive value of time where that would be 0. So later in time, that would be 0, and it would be over here, and over here, and over here. So as time gets bigger, the position x must get bigger for these two to cancel, and we get our wave. So is that a wave? Yes. All right, so again, notice, I am not saying a wave has to be sine or cosine. Could it be sine or cosine? All right, so it could be the most obvious one. And that's the one I was kind of waiting till the end. Would this be a wave? No? Right? It's not connected. How am I going to make it a wave? Is that a wave? Yes, that is a wave. All right, so hopefully you saw two things here. To be a wave, it's got to be both a function of x and t. And to be a wave, it has to have a relationship of this x minus vt. Although, I have drawn pictures with waves going to the right. Shall we go through this argument to the left? Come all the way back here to the beginning. What would be the requirement for this one to look like this, and a moment later, instead of here, I guess I'll switch to red, it is here. Yeah, this would be e to the minus x plus x1, right? And so we could see the same thing here. And so what does that mean back here? What is our general idea of a wave? Would it still work if there's a plus sign? But it would be doing what? Going to the left. So again, our general wave equation is not just a minus, but it is a plus. So again, to be a wave, this is what we call our wave equation. It can be any function. It can be Gaussian, it could be Lorentzian, it could be the trig functions, it could be logarithms, it could be anything you want. But it has to have both x and t, and they have to be connected by that little tiny equation on the inside, x minus vt or x plus vt. Either one will work. And the best thing about it is we can look real closely, and by looking of whether there's a minus or a plus, we know, is this a wave? Yes. Is it going to the left or to the right? Yes. We can see it right away in the equation. And that's what I'm trying to point out here in the math here. Yeah.
What if you had Vx minus Vt?
Vx minus Vt wouldn't give you a wave. Actually, yeah, dimensionally that doesn't make sense. You know, a v times an x. Yeah. So no.
You could put variables in front of the x and it still work.
I think what you're asking is if I just put a variable in front of the x, no. But if I put, and we will, the whole function x minus plus vt multiplied by some number, a, that would still give me a wave. I don't know what, it's supposed to be an a. Okay? So that would still have the relationship I want. And in fact, I'm about to do that. That'll give me some play with the equations.
What about just in front of the x?
No. Now, if it's just a constant in front of the x, I'm okay. But not like you said, not the velocity of it. Yeah. All right. So I better pause here, especially since a lot of you are giving me kind of a blank stare. It's like, huh? Really? And I admit, it's a little abstract, but if nothing else, get this point, especially since we're short on time here today, is look for this. Any function that has both space and time, and the space and time are connected in this way, x plus or minus vt, then it is a wave. Anything that's not that is not a wave. It could be other things, and we'll work with other things, don't get me wrong, especially when we get into chapter 18 where we start talking about what we'll call complex waves, other types of just other than our simple waves. Okay, so that's coming up, but not in this chapter. And so it's got to be x plus or minus. And if we see a minus, we know it's going to the right. We see a plus, we know it's going to the left. That's my point. And in fact, I feel like I should at least take a moment, even though we are a little bit tight on time here, to write the wave equation in a little different format, because I know many of you have used the wave equation in your differential class. Am I right? And you probably did not see it in this form. Am I right? So let's look at this a little bit closer, or a little bit different. Let me take the derivative of y with respect to x. And maybe even a little bit beyond the scope of this course. Here's what I mean if you've gone far enough in your math to do what calls partial differentials. Oh, what I really mean is take the derivative with respect to x, but treat time as a constant, even though time is a variable in the equation also. So we call these partial differentials. So treat time as a constant. See, what would happen if I did that? If I looked at this equation and I did that, I would get what I will call y prime, right? I'll just call that's the derivative. That's the derivative of the function. Now, I'm not going to say what kind of function it is, so therefore I can't take the derivative. I'm just going to say that would be its derivative. Fair enough? Let me try that again with taking the derivative with respect to the other variable, the time variable. What would that look like? Well, I guess I could write that as taking it with respect to x and then x with respect to time, right? Because this is what we just called y prime. What's this? That's velocity, right? Now, like I said, you've probably seen this. Let me go one more step. What if I take the second derivative of y with respect to x? Well, that, I guess, would be taking the derivative of this. So let me just call it y double prime. Where it gets more interesting is down here. What if I take the derivative twice of the function y? That would mean take the derivative one more time of that function, right? It's a product rule. So it is the first times the derivative of the second plus the second times the derivative of the first. Now again, looking closely at this and just doing the simple case of how does the velocity of the wave change with time? Well, I said these were waves. They're just going to go traveling at a constant speed. They're not going to go faster or slower. They're not accelerating. So what's that part of the derivative? What's this? Okay, your derivative of a constant. Derivative of a constant is 0. So that whole term goes away. Okay, fair enough. So now I have second derivative of y with respect to time equals, that one goes away, and I have this again. I have v, and I can do the same chain rule that I did before. Y prime with respect to x, and then x with respect to time. This is what we just got done calling the second derivative. This we got done calling velocity. And so what I have is the second derivative of the wave equation with respect to x is equal to y prime. Looking over here, that y prime would be 1 over the square root, over the square of the velocity times the second derivative of the wave function. Anybody seen that? Yeah, so a lot of you have seen that. So this is the same as that. Okay? And so sometimes, and your author in section 1 of the book says this is the wave equation. In the last section of the chapter, he says this is the wave equation. And if you're not careful, you finish the chapter going, well, which one of those is the wave equation? Is it 6 or is it half a dozen? I'm confused. Okay? They are the same thing. Now, the reason I say that is because many of you are in 220 right now, or you've been through 220. This is a great way to represent the wave equation, because the whole point of Math 220 is to teach you how to work with differentials and partial differentials. So that's probably why you saw it in this format. However, for us, this format will probably serve us best. So that's the format we have for this class. All right? Well, I'll keep going, because as I said, this can be a little bit abstract, but there's just some important principles that we want to make sure we nail and understand, because we're going to apply them to sound waves, and we're going to really apply them into chapter 18, and we're going to really apply them when we get into our optics. And we're going to apply them again when we get into our quantum mechanics here. And so don't be surprised we hit like mid-April, and I'll say, remember the second week of class where we wrote down the wave equation? And you'll say, of course I remember, because you warned me. In fact, it's April and I'm already reviewing for the final. No. All right. Well, maybe not that much, but you will. We will come back to this again and again and again. Watch this for a moment. Let's ask the question, what happens when two waves come together? What happens when I make a pulse and it goes down, and as it comes back I make a next pulse and they meet? Yeah, and if you remember it, the fancy word we're going to use is called superpositioning. Mathematically, fortunately, it's very easy. And if they're both up, as you said, we will call this an overlap. We'll call this an interference or a superpositioning of it. What does this look like here? And so hopefully you kind of saw it here. If I were to make a little pulse going this way, call this y1 xt, and a second wave has a slightly different shape, y2 xt. And I guess the one I showed you really didn't have a slightly different shape. It's kind of hard to make a square looking one on here. Maybe I'll draw the picture first and then I'll try it to see if you can see it. What is going to happen when they come together? So they're coming right here. What will I draw here? What will the shape of the water or the shape of those rods look like? Yeah. And this really is trying to say that waves have this linear property we call in math. What do we mean by linear property? Derivatives have linear property. Integrals have linear property. What does that mean?
Direct relationships.
Right. If I had the integral of f of x plus g of x dx, what do I mean by a linear property?
Separate.
Yeah. The separation of the two added together is the same as adding the two and then taking the integral. So I can integrate and then add, or I can add and then integrate, right? That is a linear property. And waves do the same thing. Waves have this fancy or simple linear property, at least on a simple scale they do. And so we will say we're just going to add them together. And that makes our math pretty easy. Just like that, is other than doing an integral, could be pretty hard. The concept is pretty easy. What would be the total wave then? How would I mathematically represent two waves together is my point. Now that we've just spent 20 minutes or so talking about mathematically writing one wave, how would I mathematically write two waves? Answer? Just add them together, right? The total wave would be nothing more than wave number 1 added together to wave number 2. So if you knew the mathematical description of one wave, then you just add it together with the mathematical description of the other waves. You can then add them and then manipulate them, or you can manipulate them separately and then add them, and that is what we call a superpositioning effect, an interference effect. Yeah.
So, if you had two waves that were opposite and they came to each other, should we cancel each other out and then go back to the other shape?
Yeah, I'm glad you asked. I'm going to build up to that here, but I want to build to that and just say, draw A picture, and B, the equation. And then ask, before we get to what you asked, what would happen next? What does the next picture look like in this movie? Yeah, mathematically you can hopefully see it here. Look, you can think of them as combined together and get this picture as one complicated equation, or you can still think of them as separate, and so what's going to happen is this square looking hump is going to be moving off over to here and still heading that way, and this rounded hump is going to be still here moving that way. Fair enough? And really what I want to make sure you see here is, here's how waves can be very different than the mechanics we did in 121. If this was two softballs coming together and they hit, what would happen? They would bounce back. And the one that was heading to the east would now bounce off and go to the west. Fair enough? What happens with waves? There's no bouncing. There's no material there. They're going to pass right through each other. My sound waves will go to you, despite the fact that there is other sound waves going across the room this way and this way as people, shuffle papers or whatever. And so the sound waves just pass through unhindered right by each other. The total effect may not look that this is two things until maybe later in time. And notice again, the round one doesn't go that way. And let's see if I can even come close to doing it here. The round ones are easier to make. So I'll make a rounded one. And then as it's coming back, I'll kind of make as square as I can, but hopefully look different so that you'll see what happens when they meet. So here's the rounded one. Here's the square one. Could you see it? Just say yes and humor me, right?
Just do the square.
Just do the square by itself?
Yeah.
Square. Is that square? Okay. Oh, you just want to see the square. I get it. All right. Maybe I'll try a little short hump with a bigger hump. Can you see that? And can you see how they come together? What you're going to get is, at that moment where they overlap, we are going to get an interference. We'll call this a constructive interference because both are saying push the rods up. So when you put together an up and an up means you get a total of up. And so if this is saying push the rod up 2 centimeters and this is saying push the rod up 2 centimeters, what you get is 4 centimeters. That's what this math is saying, right? The total superpositioning of it. Okay, but right in the center. In fact, I think just 2 rounded humps right in the center work really well. Rounded hump and rounded hump, when they meet, oops, got carried away there. It's not quite a perfect wave on reflection. Rounded and rounded. But right there, you kind of see it spike up a little bit, right? And of course, you guys are probably a little bit more familiar with it at the beach and watching the waves come in. You'll get a wave from this way and a wave from this way. Or some of these different places, the wedge is a good example of that, where the waves come in and bounce off the jetty and come back. And so you got the wave coming in, you got a reflection off the jetty. And when those 2 waves meet there, right there, that wave is twice as big. And so that's where you take your boogie board. That's where you take the surfboard, right? Or the pier, you get it off the pier. Ventura Pier is a really good example of that, where you get the reflection off that. The old oil piers. Well, you guys are too young. What the oil piers are? Down. When did they take them out? 98? Yeah, so you guys. Yeah. It's too bad. Great place to watch the waves. A lot of interesting effects there, but they were in danger of falling apart and falling down. So I guess that would have been worse. We'd have all that rubble all over the beach. All right. So they took them down there. But there was about a 10-year protest from the surfing community saying, "No, don't take those down," you know, and man. Anyways, but I think you're hopefully getting it. Now, finally on to your question. What about the other direction of here? Let's draw the picture the other way. It's the same logic, even harder to show with this wave machine. But if I were to take a wave that has a rounded upward hump and another wave that has a rounded downward hump and make them come together, what would happen when they meet? Yeah, and hopefully you see the same logic that they are linear functions. What I would do is I would say, okay, if I wanted to write this out mathematically, I'd say this is wave number 1. And this is wave number 2. To describe mathematically the total of those two waves, I would just add the two waves together. Now, of course, this one said up, so a 2 up and a 2 up became a 4 up. But at this one here, when this says a 2 up, but this says a 2 down, when they meet, what do you get? Yeah, you get 0. So we still call it an interference. We still call it a superpositioning. But since it's of a lesser amplitude, we call it a destructive interference. And we have less of a signal with that, if you will. You may have noticed this in a couple of places. Probably the most common one is your cell phone. You know, you have different places. On campus here, for me, it's just past the administration building. If I stand there, I can quickly see the bars on my phone just drop. I'm like, why would it drop? I mean, TV Hill's just right there. I can almost see with my eyes the satellite, or the cell site, right? Well, I'm probably getting a direct signal from it and a reflection off the administration building, and the crest of one is lining up with the trough of other. So what happens to my signal? I'd say I've got some interference, destructive interference, and my signal strength has really gone away. I walk a few hundred feet, maybe 1,000 feet, and it's totally different. I get some bars that just skyrocket off the end and go, wow, look at this signal. Because what happened there? The two signals now, I'm at a different angle, different location. The wave coming directly from the cell tower, the wave reflecting off the administration building, line up so that crest lines up with crest and trough lines up with trough. I usually don't use the word interference, but it is a constructive interference. I said, wow, this is a good place to be. I just think I'm getting a strong signal. Same thing at the beach. I wait a while. Oh, the waves are big now. Yes, big waves coming in. Well, no, all the waves were coming in before, but now the crests are all lining up. And now I've got a set of waves that come in. And so they're lining up, and I got some big waves. I don't sit out there and go, hey, look, superposition time to ride the waves, and then hang out for 10 minutes, and then wait for the next superpositioning set to come in. You know, that's not really the vocabulary, but that's exactly what is happening then on the waves. Noise canceling headphones, as we will talk about in the next chapter, is a good example of this. Stealth aircraft is a good example of this. I mean, if I go down and put on those Bose headphones and put them on there, and I get into the store and I turn on that little noise cancellation, I mean, all the racket in the store just goes away. Why? What did the engineers do? Yeah, they got a little microphone in that headset. And the microphone picks up all the noise that is going on in the store. And if this represents all the noise going on to the store, then they repeat that noise with a wave that instead of going up is going down. And so what gets to my ears? That, right? So put them on, flip the switch, place goes dead. And then I play the CD, and all I hear hopefully is the CD. Yeah.
I was wondering, do they put the microphone inside the headphone and put the attach the negative wave into your ear, or is that out?
You know, I'm not 100% sure. I'm pretty sure it's on the inside because I want to know what sound is getting into your ears. Yeah. One of the luxury cars, I think it's Lexus, has them in the you know, they got the 32 speaker sound system. It's like, really? Do you need 32 speakers in your car? But if you are going to pick up the sound from the road noise, okay, and then play it back with exactly the same shape, you're going to need a whole system of speakers to do it. And so that's really what they're after, so that you can get in the car, you can close the door, you can start driving, and then whatever noise is picked up, the microphone and then the speaker system will play it back and deaden the road noise, and you'll feel like you're in paradise. And oh, what about the? They're not that perfect, and I don't know if they've accommodated that or that perfect. So yeah. Yeah. You're gonna hear a fire truck. Yeah.
Well, it'd be tough for the noise cancellation to account for the Doppler.
Well, I suppose in theory. But the same thing works if you're an airplane. If you're an airplane, a B-2 flying into enemy territory, right? The radar comes off, hits your plane, goes back. You don't want the radar signal going back to that person who's got a missile pointing at you. So how do you keep the energy from going back? Very quickly, not easy to do, but the same thing idea. You send the radar back that is on your aircraft out of phase, and so what gets back there is hopefully a very diminished and very small return, and nobody knows you're there.
So for a moment in time, it's completely still, but there's still energy that makes me keep going?
Yeah, now, okay, fair enough. I mean, you might look at this and say, hey, it's perfectly level, where's the energy? But remember, these rods are then in the process of moving. So maybe I should have drawn a moment before they hit. What does it look like a moment before they hit? Right? What does it look like the moment after they completely overlap? I didn't line that up real well. But the point is, these rods aren't moving down. These rods are moving up. Are they level? Yes. But are they moving? So they got kinetic energy. So it's not like the energy's gone. Right? In this case, that accounts for the energy. So the positioning of them is level. Okay. If you're talking about the sound waves, then you will, as you can see from conservation of energy and from the math, that if you do set up to have destructive interference, we'll say where the driver is, then you have constructive interference somewhere else. And so the passenger maybe the passenger hears more road noise. I don't know where it is. Maybe hopefully they set it up like maybe in the back window with absorbing material, so that the constructive is someplace where nobody will be sitting, and then it gets absorbed and turned into heat. But yeah, you've got to have, if you have destructive and there's no energy, you have to have constructive to match the energy somewhere else. Yeah.
That transverse, how do you cancel it longitudinally?
Well, it's a little harder to see, but it's really the same thing. If I had rods that were saying move this way, and I had rods that were saying move this way, when they meet right here, that rod just stands still. So, okay, push me this way, push me that way, I'm going to stop. Yeah. Well, anyway, it looks like I'm getting a little bit more into exact waves, which is what the next couple of chapters are. So we're going to do all this with sound waves and complex waves in chapter 18, and with light waves as we get into the next optics, and then a little bit, not much, in 122 with radar and other electromagnetic waves here. But that's what this is after, this principle of superposition. I'm going to even try to do it for you. Not so simple. But let's see. We'll make a rounded hump and then a lower rounded hump. Maybe What does it keep hitting over here? Maybe I'll try it this direction. Keeps messing up my wave here. But if I go up and down, right there. Right there. Did you see it? And I gotta admit, that one's even harder to see than this one. I should try that one again now that I'm going from the other side. But this one is because when they get right here and then do this and do this, it's just so easy to miss this. This looks big. And that looks big. And it's just that moment right in between that it looks really, really small here. So let's see, I'll try it again. So up and down. Wait, see it? Oh, good. Some of you got the idea. Just say yes anyways. Okay. If I do a up hump and a square hump, no? Yeah, I'll leave that one alone too. So not an easy way to demonstrate it, but I think you're getting the idea. Well, let me keep going. I have been showing you so far, really most of them, the waves on the rod. Let me look at something else. This isn't exactly a string. I do have a string up here and I'll use that, but for the sake of conversation, let me call this a string. And so what would waves on a string look like? Well, I guess I could kind of, make some wave here and send it down. I guess in this case it kind of comes back. I could pull it a little tighter, right? Make a wave. I'll just make a little wave pulse. I can move in so it's not so tight. I don't know, can you see anything different here?
It's coming back reverse.
Ah, it is coming back reverse. I'm glad you saw that. More on that in a second. It's not caught him after. But look at its speed. Does it have the same speed? Does that look slower to you? Yeah, the amplitude though is probably about my hand because I'm kind of pushing it each time. But doesn't that look kind of slow? That's kind of the first step. Compared to a lot of tension. Because here's the part I was saying at the beginning of lecture. I'm going to cheat a little bit here. And just simply say that your author does a good job at this point by saying you can have waves on a string. And if I look at a couple of waves on a string, maybe I will kind of set this up right here for a second. And so here's my oscillator, and it goes back and forth. And so like this, these are the waves, right? And I could write out an equation for these waves. And they would travel at some speed. But as you can see it flex up and down, wouldn't you think the speed would be depending on how tight you are pulling that string? And it will. And so without proof, let me just put this on the board and say this is one of two to save time that I'm trying to do this in one day to say that you can certainly have waves on a string or rope, whatever you want to put there. They would have some speed, and of course their speed would be their wavelength times the frequency. But its speed should be somehow related to the tension. And it's not obvious until you go through the little proof, which, like I said, I am going to kind of skip over. But the tighter you pull that string, the faster it goes. That much seems to make sense because, that's the tension is what snaps it back. And so if you pull the string up, and you have a tight string, it's going to snap back a lot quicker when there's more tension on it. So I would expect more tension to be more speed. Now the fact that it comes out to be the square root, I'm going to kind of just brush over and say it does. So it's related to the square root of the tension. That's not the only thing though. What else do you think would determine the speed of these waves on the string? Well, with the length might determine how long it would take to get to the other side. But what I'm after here is an inertia effect, right? How heavy is this spring? What is the mass per length? And so we will say mass per length. Now, again, I feel a little terrible here about not giving you the whole picture, but I think it's better that we kind of move and see some other things here and say, look at your author. He goes through this little proof here, but he calls this mass per length, the symbol mu, and says for a string, and like I said, he goes through about a half-page derivation there, and he works out that the speed of waves on a string are, of course, related to two factors. And I just want to talk about the factors. I want to talk about these and their effect. One of them is the tension. How much are you pulling on the string? It makes sense that the more tension, the faster it should be, I trust. But hopefully it also makes sense that if the string is heavier, if the string is fatter, wouldn't that give it more inertia? So when you pull it up, isn't it going to be harder to come back down the heavier it is? So you would expect it to depend upon its inertia, and you would expect that inertia to be in the denominator. Fair enough? And in fact, this is what we're going to do in the lab this week. I think that's this week. Yeah, I'm pretty sure that's this week. And what we're going to do is we're going to put a bunch of strings. We're going to then change the tension and see how it affects the speed. We're going to change the mass by hooking up different strings and see how that affects the speed and verify if that equation is not true. So I'll say it again, very important equation. At this point, I just want to give it to you and talk about, what these two things are. I'll let you read the derivation of it, and then we'll do the lab on it this week, and we'll hook up the strings, and we'll verify that the velocity is affected. You can see it best, I think, by me just pulling on this one. If you noticed, I have a small weight hanging here. This small weight is what's giving it tension. The combination, then, of the tension and the mass per length of this string gives it its velocity. But as I said earlier, its velocity would also be its frequency times its wavelength. So, over here, I am creating the oscillations with this little electromagnet. It's going up and down. It happens to be set, you can't see it, but it's set at 13 times a second. So this is going up and down 13 times every second. So if I took that frequency, 13, times wavelength, so what would be the wavelength? Here? And I'm hoping you can see that if I took a picture of this, when it's up, would be a crest, which would mean this would be down, it'd be a trough. And so this next one would be up. And so from here to here, the center of those, that would be, I could probably tune this a little better. It keeps, better or worse? Yeah, I think that's a little better. But from here, where it would up, and then that would be a trough, and then so this would be a crest. That would be one wavelength. Or if you like, maybe from here, going up, back down to here. And as when we get into 18, we will talk about nodes and antinodes here, but I'll wane on that. What do you think would happen then if I pulled on it a little bit? Gave it a little more tension. Yeah, that should make the velocity more, right? Now you're not going to be able to see the speed because they're just ricocheting back and forth. But how about this? What would you see here? Yeah, wouldn't you see a longer wavelength? So let's give it a little tension. Get it going again. Last time I did this, I pulled it so hard the oscillator fell over there. I got a lot of weight on there this time, so I'm pretty, there we go. Is that a longer wavelength? Yeah, in fact, the whole distance is one wavelength now, right? And so there is more tension. Okay? So again, without proof, but we'll go through it in lab and make the measurements. The speed on a string only, okay? So I'm not talking about these rods. But do you notice the difference between this series of rods and this series of rods? Do they have the same speed? No. Why would you say they don't have the same speed? All right, you see it? This part down here. Now again, these aren't strings, so I don't want to take this equation too literally. But aren't those rods down, the longer ones, these? Wouldn't they have more of an inertia effect? Didn't we learn back in chapter 10 that if you had a rod rotating around its center, its rotational inertia would be? So I of a rod about center. Ah, good. 1/12 ml squared. Right? So I'm not after so much the formula, but you are seeing it that these have more inertia. These are harder to rotate. And the fact that they are harder to rotate means that this number in the denominator is bigger, which means their velocity is going to be smaller.
So would that be like, that seems to me like the substance of a medium that a wave might be moving through, like, a wave through water versus a wave through jello or...
Okay, right. So the speed of I think what you're saying here is the speed of the wave depends on the conditions of the medium. How tight is the string? Or in the case of water waves, what is the interaction between the two water molecules? Together with how massive or how much inertia does that medium have? Yes. And so the speed of any wave is going to be dependent on what is the medium. And so the speed in water would be different than the speed of air for sound waves, let's say. Different than the speed in a solid, like aluminum. And we'll see that on tomorrow, Thursday, as we look at the different speeds. Yeah. And so it depends on the tension and depends on the mass of those between them. Well, anyways, I probably also spent maybe a little too much time there already here. Let's keep going with this. There's just a bunch of things I want to make sure you see here about waves. Let's look here at really what you already saw. What about the reflection of the wave? Did you notice that when the wave got to the end of the material, it reflected? And of course, you already saw that, right? But hopefully you saw one other step here, that this up pulse, as it moved to the far side, it reflected and it was still an up pulse, wasn't it? Because watch this step here. I will take this rod at the end and I will clamp it on this back side, but I want you to see me clamp it. This rod can't move now, right? I can't lift it up because this pole stops it. And I can't really push it down. I guess I kind of could, but I'm picking up a pretty heavy weight, right? So I could, but a wave's probably not going to pick it up. Shall I try it again? Shall I make the wave go to the end? Will it still reflect? But it will be different. And watch. As the wave goes to the end, it will reflect. But it inverts. And so if it was an up pulse coming in, it's going to now be a down pulse. What if it was a down pulse? It now becomes an up pulse. Many of you saw it already with this one. Here, this one was clamped. And what did you see when that pulse came in and bounced off? Did it reflect? It did, but what happened? Yeah, the up pulse then becomes a down pulse. And so my point is this, that we can get a reflection. That makes sense. But we need to know what it's hitting in order to decide that when the wave comes back, is it going to be an up pulse or a down pulse, right? And so here's kind of the logic. Let's look at this. Why did this one invert? Why did this one invert? Maybe that's why I should use this one. But if you can imagine when this one's coming in, and so the wave is up, and it's coming up, isn't this string or spring pulling on this? But what does this material do? Pulls back, right? The fact that it's clamped, the fact that it can't move, right? Static equilibrium, Newton's third law says that this is pulling back. So if this is pulling up, this is pulling down. And if I had been standing here pulling down on it, what would you think I would make? A down pulse. Exactly. So when you hit something like this, when your wave comes in and hits something what we'll call solid, more dense than what the wave is made out of, it's going to be pulling down, that when you get a reflection, that reflected wave is going to be inverted. Fair enough? But on the other hand, what did you see when I didn't hit something solid, locked into place? When I hit something soft, low density, what happened to the wave there? Well, it's still reflected, but it didn't invert. I did not have the tug down. You don't see it quite so well with this one, but I will move it up. And so now when this wave comes in, it can just pull this up, right? This metal here is not tugging down. So it doesn't make a downward pulse. In fact, the fact that this goes up would be like my hand going up, and if my hand went up, what kind of pulse would I make? An upward pulse. And so the key here, as we look at reflections, is to realize that you will get a reflection, but the wave that comes back may be inverted or may not be inverted. We got to look at what is it hitting. So in this case, I hit something soft. There it is, soft. It reflects. No inversion. This one doesn't slide so well. I hesitate to even attempt, but why not? We're here. See what happens here. If I make a pulse, kind of got stuck in there. Huh? Oh, maybe I'm pulling so hard. That wasn't too bad. That one actually went back down. There we go. So up. There we go. But you do get the reflection. And that's my point here. You get a reflection, you just don't get an inversion. Let's add to this a little bit. Let's put the two wave machines together. What if I make a wave here and then couple them together? So I have a little metal clamp that, if I get them close enough, I can get them, there we go, together. And other than they're tweaked a little bit, what would happen now if I made a wave here or here and I sent the wave down? Maybe I'll do this side because we know they go slower over here. And so the wave comes down, the wave comes down, the wave comes down, right here. What's going to happen? So it's going to transmit instead of reflect?
It's able to go there. It's able to go there. It's able to go there faster. Faster. Frequency remains the same.
Let's try this real quick. Ready? So watch right where they meet. Did it show it enough? Did you see a reflection and a transmission? Did you see that when they meet here? Right there? They keep hitting on that side. The rods aren't well balanced. Maybe I'll do a downward pulse from this side. What happens right there? And my point is, when we have something on the other side, instead of nothing, won't some of the energy transmit through? But did you notice some of it reflected too? And watch this side. As I go from this direction, maybe I need to tweak more than just that one. When I go from this direction, if I make a little pulse here, what happens when it hits at the medium? Can you see some of the energy get transmitted? But could you also see it reflected? But it's the same idea. Look at the pulse. Let's look at this one that's going really fast, but it hits what? More dense or less dense? More dense. Are you going to get a reflection? But is it going to be inverted or not? Yeah. And so look carefully. Going this direction, I should get both a transmission and a reflection. But because this is going to something more dense, the reflection is inverted. Now, is the transmitted inverted? No. And so I want to make that clear. The transmitted will never get inverted. Watch this direction. If I go from here, it transmits, not inverted. Did it reflect? Yes. And not inverted, right? And so there will be a little bit of the energy that transmits. There will be a little bit of the energy that reflects. The key we got to look for is to remember that the reflection may or may not be inverted. The transmission will never be inverted. Don't forget that. But the reflection may be inverted. Depends which way you are going. Yeah.
In an ideal case, wouldn't all the energy go to that medium?
No. The ideal case, and maybe we should make this clear, let's say this wasn't hooked up like you saw before. When I do this, all the energy from one rod goes to the second, goes to the third. And although didn't really prove this mathematically, but the reason the first one gives the energy exactly to the second one is because they are identical objects. And so as one goes up and pulls the other, its vibrational motion is exactly the same. It's what last chapter we called a resonance. It's a perfect match. And so anytime you hit something that is not a perfect match, there will be, of course, a mismatch, and that will pull it back. So when we go from this direction, from something to nothing, there is 100% of the energy, a complete mismatch. When I go from here to here, we might say there's a 50% mismatch. And 50% of the energy goes forward, and 50% of the energy comes back. And so it depends on what we hit, too, whether it's going to be an inversion or not. And that's what I really wanted you to see. So going this direction, I hit something more dense. It should invert on reflection. Going this way, I hit something less dense, and it should be a reflection, but not inverted. Either one does send a little bit of the energy for a transmission, but none of that is inverted. Fair enough? All right, well, a couple more things, we'll be done with the chapter here, and then hopefully we can jump into a few examples, and unfortunately that might be the best we're going, quite a few more things here, best we're going to get here for today. Now, earlier on, we had said that any function that had an x, either a minus or a plus vt, would represent a wave. However, as many of you already were thinking about an hour ago, maybe the best one to describe is something that is sinusoidal, right? And so, why don't we put the most common equation on the board here, we are going to probably write most of our equations, and certainly everything in this chapter as our starting point. Let's write it as a sine function. So it must be sine of x, either a minus or a plus vt, right? It's got to have at least that much. It could have other things. For example, I'll put an A out in front. I think you're guessing from the last chapter and even from your math class. What do you think the A stands for? Amplitude, right? If I decouple these for a second, obviously I can make a sine wave that looks like this, and I might call that a small a, right? Small amplitude. Or I could make a wave that looks like that, a big A. So in other words, these are waves. It doesn't really matter if A is big or small. They're still waves, right? And A would then determine its amplitude. Here's where it gets a little more interesting. What else could happen with a wave? Well, it could look like this, where I have a long wavelength. Or it could look like this. Or I have a small wavelength. Aren't those each waves? How would that be represented in that equation? What would I add to this equation to make it look like something that repeats right there at one wavelength? When x is equal to one wavelength. And as you pointed out earlier, I can't put anything in front of the x alone without here. But couldn't I put something here? Wouldn't that still give me the function x plus or minus vt? I would still give me a wave. But that factor out in front would help me decide whether this is going to be big or small, right? If this number was big, that means that x doesn't have to go very far before I repeat. And so maybe if I did this in blue, I would say that would represent a short wavelength. That would represent a big number where that question mark is. Fair enough? But on the other hand, a wave that looked like this would mean it has a big wavelength. And that means we got to go up to a large value of x before it repeats. So this number needs to be small. So clearly that number in front is what controls the wavelength. This number controls its amplitude. And so let's talk about that. What should go in front there?
Why does the short wavelength have the smaller amplitude?
I wasn't necessarily focusing on amplitude. I could have had a small wavelength with big amplitude. That's just the way I drew it. No. Would you feel better if I, kept it the same amplitude? No. I was just drawing quick. All right. So the amplitude, as you pointed out, and the wavelength are two separate parameters. All right. So like I said, the A, I don't think many students have struggled with, but I have seen this. It's this number out in front. So to finish up the chapter and to finish up the math to mathematically write a sine wave, we need to focus on that question mark. What would it be? What are you going to need to put here so that you can guarantee all these different combinations? That is, when x is one wavelength, it will repeat. Well, let me ask, when does a trig function repeat itself?
Is it related on a period?
Every 2 pi, right? And so I'll kind of do this quickly since we're low on time, but I claim if you put a 2 pi over lambda in front, that would work. And maybe you can see it when we multiply it out. When you multiply it out, you will get 2 pi x over lambda, plus or minus 2 pi vt over lambda. More on that in a second. But do you see it here in this equation? Do you see it when x is equal to lambda? What's going to happen? They're going to cancel. What are you going to get? 2 pi. And that's what you need for a trig function, right? A trig function repeats itself every 2 pi. So the simple answer is I need a number that goes here such that when x is 1 wavelength, this multiplied by this question mark gives me 2 pi, right? That's when a trig function repeats itself. And that's what I wanted you to see. And so we will put out in front this 2 pi over lambda. In fact, let's look at this other one. Because this other one, this other part of the puzzle says it should repeat itself every period, right? And so this is very clear, and it does work. It repeats itself every wavelength. So you put any integer number of wavelengths in for x, you will get an integer number of 2 pi's, you will get an integer number of cycles. Exactly. And the same thing should happen here. And so if I do a little bit of math on the 2 pi times the velocity over t times wavelength, I can look a little closer at this. What's that? Okay, fair enough, it's frequency. What's the reciprocal of frequency? Period, right? And for me, it's easier to see this. What is this saying? This is saying when the time is 1 period, what happens? Cancels, and what are you left with? 2 pi. You're left with 1 cycle. So this number out in front, this 2 pi over lambda, is exactly what I need. That 2 pi over lambda will be a number that is related, of course, to its wavelength and related to its period. It's the number needed in order to make sure that it repeats itself in 1 wavelength in space, and it repeats itself in 1 period in time. And so it works out perfectly. And in fact, we use it so often, we give it its own symbol and its own name. And so 2 pi over lambda, we give the symbol k. And as the equation kind of implies here, this would be its angular wave number. Funny sounding name, but if you look closely at the math, hopefully it will make sense to you. If I were to tell you that from that door to that door, the distance is 10 meters, and I were to take a wavelength of 1 meter and ask you a very simple question, how many wavelengths could you fit in this room? You would say 10, but you would calculate it how? 10 meters divided by 1, right? In the abstract sense, if I were to tell you the length of the room was L, and the wavelength was lambda, and I say, okay, how many wavelengths can you fit in a room of L? You would go L divided by lambda, right? And you would be telling me that's how many waves I can fit in here, right? So if you look closely at this, what are you really trying to say? It's kind of weird looking. It doesn't have a good physical picture. It's got a great mathematical picture. That's why we use it a lot with the math and never with the physics. But what are you saying? You're saying how many wavelengths can I fit in a period of 2 pi, right? It's an angular. It's how many wavelengths can I fit in 2 pi? And so I wish I could stand up here and say, oh, it physically means this. It doesn't have a physical interpretation, but it's got a nice mathematical interpretation. The mathematical interpretation is needed with that 2 pi. The 2 pi is needed to make sure the trig function repeats itself every 2 pi. And hence we call it angular wave number, because what would you call its wave number would be something like this. How many waves could you fit in 1 meter? If I took 1 meter and divided by a wavelength, I would call that its wave number. I'd say, how many waves can you fit in 1 meter? That kind of makes sense. And so this is not 1, this is 2 pi, so we call it an angular wave number. Didn't we do that the same thing with angular frequency? What was angular frequency? 2 pi times the frequency, right? Frequency was something nice, something physical. How many times did it go up? But angular frequency was something mathematically nice. You said how many 2 pi's did it go through, right? And we could have an imaginary wheel off to the side if we wanted to do something physically. And so it's kind of nice. In fact, it makes the math reduce a little bit. And so if I call that 2 pi, let me come back over here and finish the mathematics. It kind of takes away from the physical picture, but it makes the mathematical picture a little bit easier. If you write then the equation for a wave as some amplitude sine of k times x minus or plus vt, and if you multiply this out, the first one becomes kx. The next one becomes minus or plus kvt. What is k times v? Well, k times v. What was k again? Yeah, 2 pi over lambda. Frequency was wavelength times frequency. And you end up with? Which is? Right, and so we're back to omega, because omega should simplify the math, and it does. And so again, we get a little bit away from the physical picture, but it really enhances our mathematical picture. And so don't be surprised if time and time again you don't see the equation for a wave written in terms of its angular wave number and its angular frequency. It is much easier mathematically. Annoying trying to get a physical picture from that, and so we got to back off to what is its wavelength and what is its frequency. But it is really nice in terms of the excuse me, it's really nice in terms of the equation and working with the mathematics. Well, the very last step here in this chapter is the second one. I said that I think your author did a good job of deriving it. The results are important. The derivation's somewhat important too, but I think other things I can show you are better. And so he finishes off by saying, all right, let's take waves on a string again. We already mentioned earlier that the general equation for the velocity of waves on a string is wavelength times frequency. And again, without proof, I said, you know, that would be related to the tension and the inertia of it. All right? And then he takes one more step dealing with strings. And it's really not so much about waves on a string, but really setting the stage for waves, sound waves, light waves, radar waves, so forth and so on. And so it says, look, here is a wave. This wave may be traveling at a certain speed, but because it is traveling at a certain speed, it is moving along energy, right? And so the other question we could and should ask, at what rate does the energy flow? And so had this been trying to transmit energy, I would be asking, okay, here I am shaking it, and as I shake it, at what rate is energy being transmitted down this string? Or at what rate do I have to add energy? How many calories am I burning? Right? And so what is the rate at which energy travels? And of course, going back to our mechanics, what did we call energy per time? Power, right? This is the power. Symbol P. What are the units that we used? Watts. Okay? A watt was a joule per second. All right? And again, without proof, your author says, and he breaks it apart here and says, well, how much energy flows depends on how fast the wave's going. Got to make sense. So he comes up with a V in it. Kind of makes sense. How much are you lifting it? And actually, it's the amplitude square. That I think is a little surprising. Same thing with the frequency. Depends at what rate are you shaking, and it's squared. So if the string is vibrating at twice the rate, it will have twice or 4 times the energy. And of course, it would kind of depend on how heavy the string is. The little half comes in there because of the kinetic energy. You'll see it, the 1/2 show in there when you derive it. But the point is, I wanted you to see, as kind of makes sense, that there would be 4 factors that determine how much energy is flowing down this. How much are you shaking it, its amplitude, how quickly are you shaking it, how heavy is the object being shaken, and how quickly is it flowing down there. And those are your 4 factors. As we get into the next chapter, these will be sound waves. You can see it right away when it comes to speaker design. To get a lot of energy for high frequencies, high tones, you already have that number big. So to get a lot of energy for high frequencies, you really don't have to have much of an amplitude. Fair enough? And so building a speaker that's a tweeter, getting a lot of energy there, it doesn't have to move much. How about your subwoofer? Those really, really low frequencies. Right? If you got that stereo or that surround sound system, right? You got that big box down there that's the subwoofer. The big problem is, look at that, low frequency. How are you going to get a lot of energy into this subwoofer? You got to have the diaphragm of the speaker move a lot. And I know the one I have in my living room, it's a box, it's about this long, this wide, stands about this tall. When you take off, the diaphragm itself is this little metal cylinder, and it moves a whole way. And so the engineers have designed this huge movement, this huge amplitude. In order to get a lot of energy, they've got to get that to compensate for that, to get a lot of energy into that subwoofer. And so maybe that's getting too close to the next chapter, which is the end, and we're very close to time. Should I look at 1 or 2? Yeah? Okay. I will then. And that's good, because if I let you go early, the rumor will get out that this is an easy class. And then everybody's going to want to sign up for it. And we wouldn't want to start those rumors. All right. But number 2 is my first example here in chapter 16. It, I think, lays out the general idea of these waves pretty good. And maybe I'll go, I know what I'll do. Yeah, I'll try to do these 2. These will be a good one. One is just general on waves here. Here it says right away, in number 2, it says ocean waves can be described with this formula. Y equals 0.8 sine 0.628 x minus vt. So there, they say, are ocean waves. Ocean waves can be described with this mathematical equation, where the velocity is 1.2 meters per second. And they just ask a couple of general questions. Let's see if you got it. What's the amplitude? 0.8. Good. Oh, I don't think they put it, but I think they were talking about 0.8 meters. Did they? Yeah, actually, they did put it in the formula. So the amplitude is 0.8 meters. All right. So A here is, what is the amplitude? All right, the amplitude is 0.8 meters. All right. B, what direction is this wave traveling? Okay, to the right. All right. So it is traveling to the right. What is the wavelength? All right, good. It does come out to be 10 meters here. You see it hopefully in there. That's the point. This is 0.628. That must equal 2 pi over lambda, right? And 2 pi is 6.28 roughly. That's why it became an easy calculation there. All right. So lambda, over lambda, excuse me. And so when I move that to the other side, I get 6.28 divided by 0.628, which comes out to be 10 meters. So there's our wavelength. What is the period? Yeah. So? All right, so velocity is wavelength divided by period, or period is wavelength divided by velocity. Wavelength, we just said, is 10 meters. The velocity is 1.2. I guess I will need my calculator for that one. I forgot my calculator today. But in the interest of time, I'll let you do that calculation. Could you get the frequency? Yeah, how would you get the frequency? All right, so you got the idea. The frequency is what? Yeah, 1 over the period. And so that's my first example. Again, hopefully just dives right into the wave equation. That was obviously a big chunk of this. What is the wave equation? I thought this would be a good one. Your author does a good job on number 28 here. Let's jump over to 28. And he puts this picture on the board. He takes two walls, and he takes a mass of M, and he takes a string which he calls length L. So half of it is hanging here and half of it is hanging here, and he clips the weight right in the middle. So the string is longer than the separation of the walls. The walls are separated 3/4 of the length of the string. And he comes over here and he pulls this string. He makes a little hump. And the pulse travels down and reflects back. What speed does that pulse travel? Now, what did we just learn? The speed depends on what? Tension and the density. In fact, it kind of reminds me of I was watching one of these linesmen in my backyard. He was laying out a new cable for Cox Cable, and he comes over and he pulls it. He gets up on the pole. He hooks it up. He's got this machine to tighten it, and the cable goes up, 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 up. And he's kind of wondering if it's tight enough, and he pulls out his wrench and he whacks the cable, and he boo, boo. Gets out a stopwatch. Apparently too slow, tightens it up. What was he doing? Checking the tension by the speed of which that pulse travels. So we know the speed is related to the tension and the mass density. Oh, and I think in this problem, we're just out of time here, so I think he gives us the mass density. Yeah, he does say that this string weighs 8 grams per meter. And so we know that we have 8 grams in 1 meter. Perhaps we better work in kilograms, just unless we want to get a little lost with our units there. So I will get tension in newtons, and once I get that, I can get the mass density, and from that, I can get the speed. Fair enough? And that's really the new stuff, because how are you going to get the tension? Yeah, that's back to Physics 121, free body diagram. So I can come over here and say there would be a tension T, there would be a tension T, there would be some angle theta. And as I add up the forces in the vertical direction, I would have T sine theta 2 times, pulling it up, 1 time pulling it down. That has to equal 0. So the tension would be mg divided by 2 sine theta, right? And sine theta would be coming over to here, if this is sine theta. Sine theta is this piece opposite, which at the moment I guess I'll call y, over the hypotenuse. So y over L over 2. So quick more steps and then we'll call it a go, especially since I think you got this last one. The tension then would be mg. I'll leave the 2y here. I will take this and put it up here. Here is an L over 2, so that's a 4. And maybe I'll finish with the y. The y, I guess, would be Pythagorean's theorem. It would be the hypotenuse squared minus this leg squared. So L over 4 squared, and then take the square root of that. So there's y. So put that into that, you get the tension. Put the tension into there with the mass density, you get the speed. And there's a very quick and dirty answer to a problem that should take a little while to work out the algebra. All right, well, we kind of successfully did it. So good luck on the homework. Start working on it. Read chapter 17 before you come to class on Thursday. We're going to go through these 3 chapters pretty quickly.